Welcome back to Structed. Today we're talking about composite action in beams. Now, before we get started, I want to point out that down in the links below, if you are looking to study for your FE, SE exams, or just for great desk reference material, there's a PPI 2-pass code that helps support the channel at no extra cost to you, and in fact gives you 15% off. So if you're looking to buy anything from PPI, please hit the code below. So we get into this. What is composite action? Composite action is when you take two pieces of a beam or whatever, you stick them together well enough that they work as if they were one piece. So here we've got some beam sections that are B wide and H tall. We're stacking two of them on top of each other, and we've got nothing but a tiny bit of friction holding them together. We're just going to ignore the friction because it's just not going to be enough to matter. We'll call it frictionless. How does that compare to if we've got a permanent bond between these? We'll say that this is glued. Strongly enough. Okay. So if we take our two beams here, basically we've got exactly the same loading setup and spans, and everything is the same, except that in this case, we've just stacked the two beams together. And in this case, we've done something special extra to make sure that they act compositely. They act together as if they were one solid piece of wood. This is going to be exactly the same as if you've got one overall piece of wood. But you got to make sure that you've got enough bond going on there. So in this case, we can easily calculate our maximum flexions, but the only thing that's different between one and the next is the E, or not E, I. The Young's modulus of our materials is staying the same whether they're glued together or not, but we are going to be interested in the moment of inertia. So P is the same, L is the same, E is the same, just I is different. So if we hop down here, I non-comp is simply going to be our classic BH cubed over 12, and then a second BH cubed over 12. We're not gaining anything special from these being together because it's just two of them. It's exactly the same as if we had them side by side and something put over across the top to help them split the load equally. So using two beams here, we get half the deflection that we would have gotten if we just used one. So this gives us BH cubed over 12 times 2, or BH cubed over 6. If we go I composite, again, we are assuming that we've glued this together strongly enough. It's acting just like it's one great big piece of wood here. So we've got B, that's the same. Then we've got 2H in here, cubed over 12. That's going to make a big difference getting our 2 inside the parentheses here. We've now got 8 times BH cubed over 12 for BH cubed over 6. Because we introduced some glue, some nailing, some whatever to bond these together, I comp is equal to 4I non-comp. That means that delta 1 is going to be 4 times as much as delta 2, or by gluing this together, we've reduced our deflections by a factor of 4. We're deflecting a quarter as much just because we glued those together. Now, how do you figure out how much glue is enough glue? How much glue? How much glue is something called shear flow, and in this case, if we're looking at glue, glue is rated in PSI that it can hold, so we want the stress version of this. So tau, or shear flow, our shear stress that needs to be resisted by our glue, is equal to V times Q over I times T, where V is our end reaction, or our max section shear, I guess. It's the max shear that you would get if you did a shear moment diagram of your beams, right? Q is something called the first moment of area. The I value, the moment of inertia that we typically use, is the second moment of inertia, or second moment of area, or moment of inertia of the overall shape. And T is just equal to the width of the beam. In this case, it's equal to H. B. It's equal to B. Right, so as we look at this equation, you can see that higher shears within your section require more glue to hold it together. Makes sense. Q is another section property. It's the area up here times the distance from centroid to centroid of the area that you're trying to bond versus the centroid of the overall composite. And T is kind of self-explanatory. So if you've got a wider glue surface, you don't need as strong of glue. There's also a different version of this. PSI, pounds per inch, assuming you use the right units, right? And it's just dividing both sides by T, multiplying both sides by T. My apologies. So if you want to see more about how you calculate how much glue or about shear flow, which we'll throw down right here, click this card right here, and you're welcome to come on over to the next video. Again, thank you so much for tuning in. This is what composite action is, and please like, comment, subscribe, comment what you want to learn about. Thank you so much.